So, in the last class, we discussed about different voltage doubler circuit, right? And in this lecture, we are going into more details. Okay, so let us see. Like we have seen voltage doubler circuit, right? So now we will go into more details of the circuits. What are they? This is a circuit that you have seen already, which is the Cockroft-Walton circuit, right? This is a Cockroft-Walton circuit, and we already discussed its working. Like you have this diode D1 and C1 here, and in the negative half cycle, it will get charged. C1 will get charged to plus Vm. Then in the positive half cycle, again, this it will be discharged to this, and so that uh, you will have a 2 Vm voltage here. At the point here, at the point B, as you know, once it gets charged, you will have a voltage which is oscillating from 0 to 2 Vm. But here on the D point, you will have a constant voltage of 2 Vm. So this much we have already discussed before, the single stage Cockroft-Walton circuit, so that you will get 2 Vm voltage. Now let us discuss about the multi-stage Cockroft-Walton circuit or the multi-stage voltage doubler circuit. Here also, what I want you to understand is that, like, okay, here also, what I want you to understand is that the first part of the circuit, this is the same as the our single stage circuit. You can see from C1 up to C2. This much part is same. Just in the job while drawing, we are making it look this way, but it is the same circuit up to here. Like you have C1 connected, and you have the D1 in this from this negative. What I can say secondary terminal. This terminal D1 is there. Then from there D2 is connected to C2. So this is the same circuit. So what will be the output of the circuit? Up to here, your output will be anyhow 2V, right? You already know from our last class. So up to this way you have 2 VM, and at this point, like at the terminal C1, at this terminal C1, you will have a voltage like this. You will have a voltage of what, like varying like this up to 2 VM. Right. So we have discussed like this. So we have an oscillating voltage at the end C1, and on C2 we have a constant voltage of 2 V. Right. So this much we discussed already. I think you follow, or otherwise you can go back and once see. So once you are having this 2 VM here, similar to the same circuit, similar to the same single stage circuit, we are adding such circuit again and again on top of that. You can see from the C1 means we at this point A you have a what you have a voltage which is varying from 0 to 2 VM and like this, right? 0 to 2 VM variation is there. So on that you are adding the C3 here, and similarly C5, C7, and you have the other part of the circuits here. So C2 you have C4. So once this is one stage, if you add another stage onto this, what you will have, you are adding one more 2 VM voltage here. Then you will add another 2 VM voltage from the next circuit, so that with each stage you will have what, you will be adding your voltage this way. So since we have here what, this is one stage, this is second stage, this is third stage, and this is fourth stage, right? This is the fourth stage. So with from four stages, you will have 8 VM voltage, right? Whatever that you already know. So this on this part here, it is showing the how it will be really in real. This you might be familiar with the capacitance and all that you come across in electronics laboratory and all, but these are not that way. These will be huge capacitances, and mainly we will be taking care of the how much the insulation strength of that. Okay, because it when I say 8 VM and all, it will be very high. It will be very high voltages that we will be dealing with. That is the difference. So let us get into a little bit more detail. So main point to understand here is that at point A, from your first lecture, you already know at this point A, you already know that point A, your voltage is varying from what, 0 to 2 VM. That is given here, 0 to 2 VM. And that is the oscillatory, it is having the oscillatory nature. Means your AC voltage is varying from 0 to 2 VM. And at point B, we have a constant DC voltage of 2 VM. right? So similarly, if you see what I'm trying to say is that across C1, C3, C5, and C7, we will have an oscillating voltage, and when you see C2, C4, C6, C8, you will have a constant DC voltage. Okay, so that is given here. Understood. So because of that, these two, when you are seeing the real original Cockroft-Walton circuit, it looks like you will have two capacitor columns on two sides, right? One capacitor on top of that. A column of what capacitors on one side and another column of capacitor on the other side. The column corresponding to the C1, C3, C5, C7, this is called as the oscillatory column, and the capacitance corresponding to C2, C4, C6, C8. This particular column is called as the smoothing column, because whatever oscillatory voltage you are having here, the C2, C4, C6, C8 is smoothing into a constant voltage of what? This 8 Vm. In a practical case, you will have some difference, but it will come nearby what? It will come nearby uh, it will come nearby atrium, right? This we already discussed. So may another part is that between these capacitors, since you already have 2 Vm here and here your potential is 4 Vm, so the variation will be that way. Means here maximum voltage is 2 Vm, here it is 4 Vm. So the variation will be that way, 2 Vm to 4 Vm, 4 Vm to 6 Vm, 6 Vm to 8 Vm, and similarly on the other side the other way. So this is the main point. So let us summarize this Cockcroft-Walton circuit or using this the thing. One thing is that it is asymmetric, right? That is how we defined it. And as I said, this capacitances are formed two column. One is called as the oscillating column, another one is called as the smoothing column. The maximum stages, how many maximum stages it is possible? Like seeing the design, you might think that we can go for any number of stages. Like 8 VM is there, then why don't we go up to like 10 VM or like 20 VM? Having a 10 stage structure, we can have 20 times the output voltage, right? So, but that is not possible. The maximum stages usually is where we normally go up to only 4 stages. That is like the maximum. Problem is that whenever you increase a stage, then your insulation requirement, right? So when I say the 20 times VM, you have to withstand, then that much is the insulation requirement. Insulation requirement also is high, so that creates a problem. More than that, as you know, like maybe somewhere used most it comes right. Like you cannot have when you have a diode, like it's basically semiconductor material. So when you have a diode, you cannot really have two identical or ideal diodes. There is nothing like ideal diode, or there are no two identical diodes. So that itself makes what? So you will not have your voltage to be what I can say, the voltage drop to be same at each diode and load. So that will affect. So due to this, that is the one main problem. Due to this effects, we usually don't go for more than 4 times the voltage level. Okay. Now, the next part is the symmetric voltage doubler circuit. Okay, as we were till now we were discussing about the asymmetric voltage doubler circuit, because okay, why it is so? The main part is that let us see the working of this thing. Then you will understand. So this is your AC voltage, the primary terminal of the transformer, and this is the secondary terminal of the transformer. So you will have what? You will have a AC waveform here, right? So you will have an AC waveform here like this. So it can be the positive half cycle or the negative half cycle. So any one of the half cycle, what I can say, if this is a forward bias, like let me say this potential is like this, and let me say this is forward bias. Under that condition, what will happen? Under that condition, if it is forward bias, then your capacitor C1 will get charged. Right. So if the diode is conducting, since the maximum voltage is what? Vm. Since the maximum voltage is Vm across this terminal. Okay. Let me say here and here. So across this terminal, if the maximum voltage is Vm, then your capacitor is getting charged to Vm. That is in the first half cycle. Right. Means whenever your D1 is forward bias, your C1 is getting charged to plus Vm. Now in the next half cycle, just after that, in the next half cycle, what will happen? Your D2 will be forward bias because it is connected that way. This one way and this is connected in the other way. So any of the half cycle, one among the diode should be forward bias. So on the second half cycle, your D2 is forward bias, and because of what will happen, your C2 will get charged to plus Vm. So your C2 also is getting charged to plus V, right? C2 gets charged to plus V. So if you take what you are going to take, you are going to take output between this point and this point, and you will get the voltage doubler circuit, right? You are getting the voltage multiplication part here. Your total voltage will become 2V, right? So why it is called symmetric? The symmetric term is used because as you can see here, in the positive half cycle, one diode conducts. In the negative half cycle, also what it is conducting. So here, this identical conduction of diode is there, not like voltage, our Cockroft-Walton circuit, right? So because of that, this is called as the symmetric voltage doubler. And main point is that due to the symmetric conduction of the two diodes in positive as well as in the negative half cycle, the thing is that you don't have transformer core saturation here. So there is no problem of transformer core saturation. Okay. So there is no problem of transformer core saturation here. That is one main factor. Then another thing is that if you take on like when it is forward bias, you have like 0 to Vm only. But when it is reverse bias, as you can see, it will have this diode D1 or D2. The peak inverse voltage will be 2 Vm. So you should take a diode which is having the peak inverse voltage of 2 Vm. So just simpler part. And the it, that is the simplest path. So you can have 2 Vm. So that is right. Now let us see the symmetric voltage doubler circuit in like multiple stages. Okay, this is we discussed about what one stage. Here we have multi-stage. Okay, this is not just symmetric. It is what multi-stage. Okay, we have two stages here. So this is multi-stage. Multi-stage. Okay, it's quite hard to write multi-stage voltage doubler circuit. So in this what we are doing, I think this much part you are aware of, right? So here if you take between these two terminals, if you take, you will get a voltage of 2 Vm. Okay. These two capacitances C1, C2, it is connected in series with the C3, C4. Okay. This also is another symmetric voltage doubler circuit. So by connecting the C1, C2, by connecting the C1, C2 and C3, C4 up to this in series, we are able to get what we are able to like we are cascading it, right? We are cascading the symmetric voltage doubler circuit in several stages. The problem is that how can we give the potential for the next transformer? Okay, like let me say, let me say, uh, you have, let me say, you have. Uh, if you have giving this kind of AC connection directly to the transformer without T3. So what is the need of this isolating transformer? Like without T3, if we directly connect this to T2, the problem is that you see at this point we have what will be the potential here? You will have a potential of Vm on the a DC potential is there, right? DC potential of Vm is there on the secondary side. But when you come to the secondary side of this T3, you will have a potential of what Vm, and up to here. Up to here, you are having a potential of 3 Vm. Right, so you have to you need what to withstand it for 3 ABM. So if you are directly giving that potential, then you should be giving the insulation which is having the capability to to hold it till 3 ABM. So in order to avoid that, we are using what we are using an isolating transformer in between. Just like we take the supply and give, but through another transformer. So definitely that increases the cost, right? So it will become what it's a problem only, like the cost will increase or even the size also will increase. So this T3 serves the purpose of what to share the high voltage stress, and that is the isolating transformer used here. So there is a design problem here. Now what can we do? That is made with the improved symmetric voltage doubler circuit. So what do we do with this improved symmetric voltage doubler circuit? It is quite simple. So you have the circuit here. So instead of having another transformer, isolating transformer on the here, you have three windings. Like this is the first one is the primary winding. Then second, this is our normal high voltage secondary winding, and you have an again a third low voltage tertiary winding also. This tertiary winding is feeding the next transformer in the next level, and it goes on like that. Okay, so you have three windings. So you don't need another isolating transformer. Those three windings are already inside there. So this is the way we can use voltage doubler circuit in multiple stages, like you can see here, right? So like you can see here, this is what we are having 8 VM, and we can go up again. The restrictions apply, means the restriction here comes mainly due to one more thing. Like as you can see, in the last one we have what we were having, the supply is fed through another transformer, but here the supply is given for all other transformers. For all other transformers, the supply is given from what? From the first transformer. So how much energy, the lot of energy is supplied by the first transformer, so that will make a limitation on the this voltage developer circuit, right? So these are about high voltage DC generation, and then one more is the which is the Van de Graaff generator. You already studied it in your higher secondary classes. The same procedure it is, and I have given some note also. So your assignment, your first assignment is that to one is to explain the working of Van de Graaff generator. You can go a little bit far to understand how practically they are applied, and even you can see what are the applications of Van de Graaff generator. And then the second part of the assignment is since we have studied this voltage doubler circuit and Cockroft-Walton circuit, and we discussed what is the effect of frequency. So I will give you classroom. I will give you a link for the virtual high voltage lab provided by IIT Kharagpur. It is there, and there they have given two experiments: voltage doubler circuit and Cockroft-Walton circuit. So you have to go through that, understand the experiment, and see what is the variation of DC or voltage output and ripple voltage when you are varying frequency. We have already discussed what is the effect of frequency. I want you to plot that variation of in DC output and ripple voltage with respect to frequency. Okay, I don't expect you all to come with the same result, because you can give different values, you will get different plots. Even though even though there's a different characteristic, but not different characteristic, but you will have different plots. So do that. It's an activity, and that is your assignment. That is for your assignment, and the link I will be giving in the so with this our first module is complete, and the next class onwards we will get into the second module, which is high voltage AC generation. So high voltage DC generation is over. We will get next into high voltage AC generations. Thank you.